Welcome to this video on probability and basic counting. Here's our first example. Suppose you're at a restaurant where you have to choose one item from each of the three columns here. The question here is how many different meals could you order under these circumstances? The fundamental counting principle, which we'll discuss more in a moment, will help us compute this. But before we get to that, what if we were just to count the meals manually by listing all the choices that we could possibly make? Let's do that first. Here's the first meal we could choose. Watch the tally marks as they appear. Here's another possible meal. Here's one. Here's another one, and so on. At this point, I've counted 12 meals, but you'll notice they all involve beef. And logically, you could figure that I could make the same number of meals out of chicken, so that should add 12 more. Here's a meal. Here's one, and so on, for a total, as you can see by the tally marks, of 24 possible meals that you could make here. But it's a little cumbersome to count them out that way every time, and so it's easier to use the fundamental counting principle. That principle states that if you have independent choices to be made, and you want to know the total number of choices, you just multiply the number of choices together for each of the individual sub-choices that you're making. In other words, in this case, we have 2 choices for entree, 4 choices for a side, and 3 choices for a drink. And if you multiply those together, you will indeed get 24 and save yourself from having to actually count them out, as we did with the tally marks there. The fundamental counting principle can be modified even for events that are dependent. Here's an example. Suppose you have a team and we have to choose 3 people out of 12 on that team for specific tasks. Question is, how many ways can these choices be made? Well, using the modified fundamental counting principle, you could say that we have 12 choices for captain, meaning it could be anyone on the team. But once that choice has been made, there are only 11 choices left that you can make for the assistant. And once that choice has been made, you only have 10 choices left for the lonely bench warmer. The other 9 players don't have a particular role, so we'll stop the calculation here, multiply those together, and find out that there's over 1,000 choices that you could make in this particular circumstance. Next, we're going to look at something called combinations, which refers to the number of ways a subgroup can be chosen out of a larger group. We'll look at a small example here. Suppose we have 5 people in this group and we're going to randomly choose 3 of them. Question might be, how many different ways can we make this choice? Or more specifically, how many combinations are there? Well, there's a formula for this, but before I get to it, let's manually count out all the combinations by just picking every possible selection of 3 people. Here's one selection, which I'll list here. Here's another selection, which I'll list here. Here's one. Here's one. And what I did here is go through all the possible combinations of 3 people chosen out of this group of 5. And there they are. Now, it would be annoying and cumbersome to have to count these manually every time, especially if the groups were larger than the small one we have here. And so luckily we can rely on a formula to find out that there are 10 ways here rather than to write them all out. The shortcut is called the combination formula. In this formula, the capital C just stands for combination, stating that we're selecting a subgroup out of a larger group and calculating the number of ways that choice can be made. N stands for the total group size, which in this case is 5, and R stands for the size of the subgroup, which in this particular example is 3. Plugging 5 and 3 into the formula and working out all the math, canceling like factors and reducing ultimately leads to the same answer we got before, which we already knew going into this calculation, that there are 10 ways to choose 3 people out of a group of 5. By the way, if you've never heard of it, the exclamation point in these problems is pronounced factorial. And you can tell by the numerator, for example, that 5 factorial is 5 times 4 times 3 times 2 times 1. And in general, factorial means the product of all numbers down to 1. Here's some other notations for combination rather than the one we saw here. So be on the lookout for those. A permutation is like a combination in the sense that we're trying to calculate the number of ways that we can choose a subgroup out of a larger group. But a permutation also involves a rearrangement. So whereas a combination, which we saw earlier, is the number of ways, or refers to the number of ways that you can choose a subgroup out of a larger group, a permutation refers to that same selection with a rearrangement involved. And to give you a concrete example, let's look at the same 5 people we looked at before. You'll recall from the previous problem there were 10 combinations on how we could choose 3 people out of this group. But what if we were then rearranging them in different orders? Such as in this particular combination here, here's one rearrangement where you see that Bob wins first place, Jim is second place, and Sally is third. Or here's another rearrangement where Bob still wins first place, but Sally wins second and Jim wins third. And if you think about it, there is actually turns out to be 6 different ways to permute or rearrange these choices for every single combination. And in this particular example, it turns out there are 6 rearrangements for each combination. And if a permutation is if the permutation total is the number of ways that we can choose and rearrange a subgroup from a larger group, then you can see in this case that there would be 6 rearrangements for each combination times 10 combinations, or a total of 60 permutations here. But of course, we don't want to list them all out or write them and try to use this kind of logic every single time we want to know how many permutations there are. And so instead, we'll rely on this formula most of the time. The capital P stands for permutation, N stands for the total group size, which in this case is 5, and R again stands for the size of the subgroup that is going to both be selected and rearranged in a permutation. So 5P3 tells us how many permutations there'll be. Plugging in 5 and 3 to the formula, using what we know about factorials and canceling like factors, leads us to what we had already calculated manually, that there are 60 ways to choose and rearrange or to permute 3 people out of this group of 5. And while that certainly suffices to compute the number of permutations, it's worth mentioning another thing we could have done here is asked in sort of a modified fundamental counting principle way. We could have said, well, in this group we have 5 choices for the winner, 4 choices of whoever's left for second place, and 3 remaining people to choose from for first place, multiplying those together and of course getting the same result. I'm not suggesting you have to do it that way, but it's an interesting perspective to see how the same number can be arrived at so many different ways. Let's take a look at this problem, which doesn't exactly fit the mold of the fundamental counting principle, nor combinations, nor permutations, but rather it's a mixture of ideas put together. In this problem, we want to choose or calculate how many different pizzas can be made at this restaurant with 4 toppings out of their list of 9, and given the crust options that we have. So it appears to me that we have 2 independent choices to make here, the crust and the toppings, and I'm going to use the fundamental counting principle to figure out the total number of pizzas I can make. Obviously, there are 3 choices for crust, as we can see in the problem. But as far as toppings go, I need to figure out how many toppings there are, or I should say, how many ways I can choose 4 toppings out of 9 in order to multiply that by 3 and get the total number of pizzas. Well, the number of ways I could choose 4 toppings out of 9 would be 9 combination 4. Why combination and not permutation? Well, I'm not choosing and then rearranging them. In other words, we wouldn't consider a pepperoni, onion, mushroom, sausage pizza any different than a sausage, mushroom, onion, pepperoni pizza. In other words, rearranging the 4 objects we've chosen out of 9, or permuting them, doesn't give us a different pizza. And we're not interested in the number of ways we can rearrange, simply the number of ways we can choose 4 toppings out of 9. And that you can use the combination formula for and get an answer. And so what I know now is that there are 126 ways I can choose toppings, given that I have to choose a 4-topping pizza per the problem. And there are 3 different crusts I could choose for each. So multiplying those 2 together by the fundamental counting principle gives me a total of 378 possible pizzas, at least possible 4-topping pizzas at this restaurant. So far in this video, we focused on counting things. How many ways can this or that happen? And of course, for that, the answer is always a whole number. But now let's shift gears to the topic of probability, which measures the likelihood of an event. When we do that, we always measure the probability on a scale from 0 to 1, where 0 means that the event cannot happen, it's impossible, and where 1 means it is 100% guaranteed to happen. And anything in between could be a measurement of a probability. Here's an example. Suppose we have 34 students in a class and 2 of them happen to be named Bob. What's the chance of, if a student is chosen at random, that they're going to be named Bob? Well, such a probability would be 2 out of 34, of course, since there are 2 Bobs out of 34 in the class. This fraction reduces to 1/17th, and if one wanted to, one could compute that as a decimal on a calculator, or even convert it into a percentage. In most mathematics classes, depending on the instructor, of course, you're not likely to answer as a decimal or percent, and in particular in my classes, we should always answer as a reduced fraction, such as 1/17th in this case. Here's another example. We'll take a look at the 2 dice problem. You're probably familiar with the game Monopoly, or such games where you roll 2 dice, add them together, and move the piece. The question here is, in such an environment, what is the probability that the 2 dice would add up to 9 or higher? The bad news about the 2 dice problem is that there really is no formula for it per se. One simply has to list all the different outcomes and decide how many of these are 9 or higher. First of all, you'll notice I've listed each one as an ordered pair, representing the 2 dice. And you can see here that there's 36 different possibilities that can happen when you roll 2 dice. But granted, you can only get a number between 2 and 12, as you'll know having played Monopoly if you have, or just rolling 2 dice in general. But there are different ways to arrive at the same number, so there's a total of 36 possible outcomes on the 2 dice problem. All we have to do here is answer the question, how many of these result in a total of 9 or higher? And if you look around in the grid, you'll see that there are 10 of them. Count the yellow boxes, there are 10. 10 out of these 36 outcomes do in fact have a total of 9 or higher, and therefore this probability of getting greater than or equal to 9 would be 10, representing the yellow squares, out of 36, representing all the squares in this grid. Reducing the fraction gives us the final answer. Let's now turn our attention to what's called an AND problem for independent events. Suppose there are 2 separate events, and we want to know the probability of both of them happening. What this formula here tells us is that all we have to do is multiply the individual probabilities together. Here's an example. Suppose we're going to roll a 6-sided die and pick a card from a standard deck. We want to know the probability that the die is 3 or lower, otherwise known as lower than 4, and that the card chosen is a face card, such as a jack, queen, or king. Well, if we want to compute this probability, we simply multiply the two probabilities together. 3 out of 6, or 1/2, is the probability of rolling a 3 or lower, as prescribed by the problem. 12 out of 52 is the probability of picking a face card. You may not have this memorized, but it turns out that there are 52 cards in a deck, and 12 of them are face cards. 4 kings, excuse me, 4 queens, and 4 jacks. So, multiplying those two together by just doing some simple arithmetic reduces the fraction, and that's the probability of both of these events happening. You can see that the probability is pretty low. 3 out of 26 is not a particularly likely event, and that sort of mirrors the fact that if two events are going to happen, they're less likely that both of them will happen than either one of them individually. Now we're going to take a look at something called complementary events and repeated events. We'll start with the repeated event as shown here in the top problem. A couple wants to have 4 kids, and what's the chance that they're going to have all girls? Well, the probability of 4 girls, or that event repeating itself 4 times, would be 1/2 times 1/2 times 1/2 times 1/2, which works out to 1/16. Why? Because if we want the probability of an event repeating over and over again, or even different events happening in succession, we multiply their probabilities together. So as you can see, it's not very likely that a family of 4 would have all girls. You could express this as a percent in some classes. If you're taking my class, you probably wouldn't do that. Let's talk about complementary events. And complementary events are 2 events which exactly one of them must happen. Not 2 and not none. For example, it's going to rain tomorrow and it's not going to rain tomorrow. Those are complementary events. One of those 2 things will happen, and only one. To look further into complementary events, let's examine the same couple with 4 kids, but ask a different question this time. This time we'll ask, what's the probability that the couple will have at least one boy? Now notice at least one boy doesn't specify if it's 1 or 2 or 3 or even all boys in the family. Well, the long and arduous way to do this problem would be to figure out each probability separately, because at least one boy could mean exactly 1, 2 boys out of 4, 3 boys and a girl, or all 4 boys. But it could get pretty messy trying to compute all of these. So I'm going to use the concept of complementary events to compute them. The probability of getting at least one boy would be 1 minus the probability of that not happening. What does it mean to say that the family did not get at least one boy? Well, it means they have all girls. Simply put, if there's a 1 in 16 chance, notice the top problem here, if there's a 1 in 16 chance of having 4 girls, then there must be a 15 in 16 chance of that not happening in a family of 4. And what does it mean for a family of 4 not to have all girls? Well, that means they'd have at least one boy. So this is a fast way to compute something that might be messy otherwise, if we had to delineate all the different combinations.